I've started recording, so please go ahead, Yassi.
Okay. Good morning, good afternoon, good evening, everyone, depending on where you are. I'm Yassi Mogedam. I'm the Executive Director of International Society of Society Professionals, and we're one of the sponsors of the CFIC calls, and we promote service innovation, and that means teaming of AI and people, and very happy to be sponsor of these calls. Thank you so much. I'm being brief, Susan.
Thank you, Yassi. So now I'll hand over to Irina. So I'm going to stop sharing, and you can start sharing. Great. I can see your slides now, Irina.
Great. Let's go ahead then. Hello, everyone. I'm Irina-Maria Nicolae, and I work in research for IBM in Ireland. I'm part of the AI and machine learning core research team here, and today I will be talking about adversarial attacks against AI. So what are these attacks that can be done against AI and machine learning models more specifically? So just to set the context a bit, machine learning is trying to produce prediction models relying on data. So basically what you would want to do is to be able to predict future events or properties of unseen objects based on data that you have seen in the past. So the way this is done is through two steps. The first one is training, which will generate the prediction model that you'll be using afterwards. So this training step is done on that previous historical data that you have seen before. And the model is shown all this data. In this case, the top half of the slide, in this case, we'll be showing the model images. And we will also be showing the model what is the expected output for each of the images. So once this step is done, what you have is a prediction model that is able to function and operate. And at this point, you can pretty much even throw away the training. So at this point, we can move on to the second step where the model can actually be used to do predictions. So when we show the model images, we expect hopefully the correct predictions. In this example, we have a bird, and we would like the model to predict the bird. Now, machine learning models have found recently a lot of success, especially through the power of neural networks and deep neural networks. But it turns out that these methods, and neural networks in particular, have a vulnerable spot in the form of adversarial examples. So here, take the image to the left that will be predicted by a deep neural network correctly as a giant panda. Now, on the right side of the slide, you have an image that to us looks identical to the one on the left. But what happens in between is that we add what is called some adversarial noise. So that's the image in the middle. This is completely undetectable to us, but this will actually make the model take the wrong decision and believe that it is something else and make the wrong prediction with pretty high confidence. And this is true for neural networks and most types of machine learning models. Now, something that's particular about the noise that we add to the image is that this is not random noise. These prediction models are pretty robust to noisy images, and they're still able to output the correct prediction. But this noise has been especially crafted, engineered to make the model predict in the wrong way. Now, you can imagine how this is impactful for real-world examples where machine learning models would be used. So consider here a camera that's placed on a car, maybe for the future application of self-driving cars, right? And here, what the model is trying to do is to segment the image into what's seeing, so pretty much detect objects. Now, to the top images, you can see that it detects correctly that there are pedestrians in the image. Now, the lower half, the input image has received the adversarial noise, like in the previous example, and now the model is unable to detect pedestrians anymore. So that's the red category. So you can see right away how this can be very dangerous. For the same application of self-driving cars, here you have 2 stop signs in pretty poor quality, I'll give you that. But you can't really tell which one is the true image and which one is the adversarial one, right? In this case as well, the model will be unable to recognize the stop sign as being a stop sign, and the car will not stop. Another example comes in the form of all the personal assistants that use voice commands that are now available on the market. These have all been attacked with what we call silent voice commands. So basically you will have a command that's played back to the assistant that humans cannot hear at all, but that will make the assistant react. So I practically seen the example done with Alexa, and they're making it order stuff off of Amazon, and in the end it tells you the price and the delivery date. So why is this happening? Now, again, as I was saying, here we'll be focusing, this is happening especially for the case of deep learning and deep neural networks, but it generalizes to other machine learning models. So you have your prediction model, right? And you would want to give it input and expect the correct output from it. Now, the way neural networks work is that they are made out of neurons, which are just some mathematical functions that are composed together. Now, internally, these neurons are stacked in layers, and what happens is that you put your input at the front layer, and this input gets propagated through the layers until the output layer. Now, in the case of images, the input layer has as many neurons as pixels you would have in the image. So basically, each neuron receives 1 pixel as input. The output, when you're trying to recognize objects in images, you would have 1 neuron per category of objects that the model is capable of recognizing. And again, the neurons are just mathematical functions, and through composition, the information moves forward from the input layer to the output layer and to the correct decision. And this is what happens when we input our, say, panda image as an example. Here I've put different levels of intensity, which would be the numerical values that go through the layers. And in the output layer, the neuron that would light up the most would be the giant panda with a score of 84. And we will consider the maximum value as being the correct decision. Now, when you input the adversarial image, you have made some small changes to a few of the pixels in the image. As the information moves forward through the layers, this small change that we do not detect visually gets accumulated over the layers, and in the output layer will result in the incorrect decision function, because now the class capuchin has a higher value than the class giant panda. Now, neural networks are known for their very good discriminative capacities and their capacity to recognize multiple categories of objects, but it's their sensitivity to the input that gives them this high discriminative capacity, and that makes them vulnerable to adversarial attacks at the same time.
So to understand a little bit how adversarial attacks are possible, let's take a 2D representation of how the model sees the world. So consider here, we're not trying to distinguish thousands of objects, just two types of objects. Yellow crosses from orange crosses. So here the crosses are the data that we have seen during the training process. And this data comes from what is actually the true data distribution. So what would the set of all valid data would be in the form of the background color. Here the red line represents the actual decision of the model, which means that if a cross is on the upper side of the red line, it will be considered from the yellow class, and if it's on the lower side, it will be considered from the orange class. And you can see that the red line is consistent with all the crosses we've seen. It separates very well the yellow crosses from the orange ones. Now, what happens is that you can also see that the red line doesn't exactly match the background colors. And this is how the space of adversarial examples is created. So the noisy images that are not correctly classified by the model are actually part of this gap between how the model sees the world and what the space of the valid data is. So here I've drawn them with orange circles. When working with neural networks and when considering images, you're not really in the case of a 2D representation as we see here, so only two axes and crosses. Basically, images are high dimensional, and neural networks also use high dimensional representation spaces to, say, understand the data. So if you would this is why adversarial attacks with random noise do not work, because if you just add random noise to images, the probability of you actually pushing the image over the red boundary in this drawing is very, very low. So this is why the idea of crafting adversarial examples is to take a valid image, in our example, the image of the panda, and to add just the necessary noise that is able to push that image over the red line in the correct direction, right? So it gets misclassified. And this is how these attacks work in practice. They start with the correct input, and they add they search for the noise that will make the decision shift. So then, one of the first types of defenses that was proposed against these attacks was to incorporate the adversarial data as part of the training process. So if for example, we take the panda image with the noise and show it to the model and tell the model you are expected to predict panda for this image, the model will learn from this and it will comply. So here, if we include the adversarial data in the training process, so the circles, the decision boundary will shift to account for that data. But the problem with high dimensional spaces is that there will always be a gap between what the model predicts and the actual distribution of the data, because it is impossible in high dimensional spaces to explore all the directions and show the model all the data that it could possibly have. So there will always be new directions in which adversarial examples can be created. So this is pretty much the problem of adversarial attacks, and so far in state of the art we have very efficient attacks that exploit this idea of taking a correct input and adding just the noise that is needed to make the model fail. And on the defense side, we have seen maybe almost in the hundreds of papers proposing different defenses that can be used to reinforce machine learning models against these attacks. Now, the problem with that is that this is at this point not a solved research problem. So all the defenses that are out there only work as partial solutions to the problem. So only under certain conditions or only against some attacks. So the research on this topic is still ongoing. Now, I'm going to move on to the topic of the Adversarial Robustness Toolbox, which is a toolbox that IBM has open sourced a couple of months ago, and that is trying to address this problem. So here you have the GitHub link where you can find the toolbox. It is a Python library that is trying to fulfill exactly this gap of providing a benchmark environment for people who are interested in adversarial attacks. So on one hand, you will have an implementation of most of the state-of-the-art attacks. And on the other hand, you will have defenses and detection methods that can be benchmarked against the attacks, and some robustness metrics in order to allow people to assess the robustness of their machine learning model. So in its implementation, this library is trying to be framework agnostic, which means that you can bring your favorite machine learning model, be it in TensorFlow or Keras or PyTorch, and you will be able to use it in this library and craft attacks and try out the defenses on your model. For now, the library is focused on image data, and yeah, it was open sourced in RSA last month. So what the library contains so far is this list of methods. So you, as I was saying, on one hand, you have quite a number of attacks, and then on the other hand, some defenses as well. Many of these use this idea that I've shown you of taking, of incorporating adversarial data into the training process through different heuristics. And some of them are more like pre-processing techniques, which are trying to remove the noise, the adversarial noise from the images before they actually go through the machine learning model. So for now, we're supporting TensorFlow and Keras as backend. PyTorch will be out soon as like maybe before the end of this week. And we will soon support MXNet backend as well. And in terms of metrics, what we have so far are a few metrics that allow, as I was saying, to measure the robustness of the method, either when it's under certain attacks or just as an intrinsic property of the model. This is also, this question of metrics is still an open research topic as well, because it is very hard to evaluate the robustness of a model against adversarial attacks with only one number. So this is why we're providing multiple metrics that shed some light into different aspects of the model. So the Adversarial Robustness Toolbox is not the first library to do this kind of an effort of bringing multiple methods together. CleverHunts and Toolbox are two other similar toolboxes. But I would say that these two mostly focus on attack methods, while we are actually focusing on the defense side, because we think that it is important to be able to provide reliable AI models. So here's a quick example of how you would use the toolbox. So at the beginning, you just have some import statements, and then we're just loading the MNIST dataset, which is the standard dataset for recognizing digits, handwritten digits. And then you are able to load, for example, a Keras model, or otherwise you can create it yourself and train it. And then what you would do is just create a Keras classifier wrapper on top of that, that Keras model. This will allow the integration with the library. And from that point on, you are able to perform an attack. So here we take the Carlini L2 attack. And when we do generate and provide it with some images, we have basically obtained adversarial images out of the test set, X-test in this case. And based on that, you can further on compute some metrics and print them and use them as information. So the takeaway from this would be that the problem with adversarial examples should be solved before we trust AI and use it in practice. As I was showing you in the examples, most of machine learning models that have been completely used and exposed to users so far have already been target to adversarial attacks. So especially when important decisions are made by those models, the models should not be potentially susceptible to adversarial attacks. And about the Adversarial Robustness Toolbox, you can just go and check it out. There's also the documentation that goes with it, and we would be happy to have your feedback about it.
Thank you so much, Irina. There are one or two questions for you in the chat.
Yes.
One is asking how effective are these methods would be against ensemble methods. How effective these attacks would be against ensemble methods.
So ensemble methods was also one of the initial ideas to provide as a defense. It turns out that if the attacker considers the ensemble as the target of the attack will still succeed. Now, since then, the research community has gone through a few iterations, and now we are able to use certain ensemble heuristics that are a bit more robust against the attacks. But again, this is not the problem has not been solved.
Okay, we'll see if there's any more questions, but someone has just said that his team is about 1,200 people, and he's going to present this material to them and the links.
Okay.
That's amazing. So is that a team in Cisco, I'm guessing, right, Mark?
Yes, that's correct. It's company wide. We all deal with these various types of topics and everything, but it's a very large group that what I'll do is I'll pass the links along to them, but I'll do a presentation and let them know that this is out here.
Great, thank you, because we'd love people to join in working with us on the toolbox, right, Irina?
Yeah. It would be great to have a community built around this topic.
Yeah. Oh,
yes.
Yeah. It's something that's very. I mean, these types of topics are becoming very, very prominent in our space. But yeah, I'll definitely present it to them next week.
Excellent. And then there's another question for you, Irina. On MNIST, how does the accuracy compare with DL methods on image set with and without adversarial attack images in sample?
So with or without the adversarial attack?
Yes, with and without the adversarial attack images in the sample. Can you see the question?
No.
In the chat. If you look for the chat, you can, if you move your, it's probably near the top. If you move your mouse up the top or the bottom, you'll see chat.
Yeah, it's not really popping up. I think screen sharing.
Three dots. Can you see 3 dots and more? No?
No, but yeah, about that. So if it's in the case of attacks, basically models that normally perform, have more than 90% accuracy, drop on adversarial examples, they drop close to 0%. So basically they are unable to recognize any of the images anymore.
Is that okay, Sandkur? Did that make sense? Shall I try and unmute you so you can discuss? I've unmuted you, I think. No, I haven't. Can't seem to unmute you. Is that okay? Did Irina? Oh, question is the opposite. So Sankur, the questioner is saying you've answered the opposite.
Oh, what do you mean?
If you're
training on the adversarial data?
Sankur can unmute himself. Question is the opposite. If in training set I include and exclude images with and without adversarial attack.
Right.
Yes.
So basically if you train on adversarial data, then later this will make the model more robust against the adversarial images generated on that first original model, like before you retrained. But it turns out that in practice, your newly trained model with adversarial images will actually even be more sensitive to attacks than before, in the sense that you would need to introduce even less noise than on the original model to make the model fail. I hope that answers the question. I mean, this is pretty counterintuitive, but I think one explanation for that would be that normally what you would want in a model is some smoothness properties. So you don't want your model to vary sharply in a small neighborhood. But when you're adding adversarial data, that adversarial data is actually close to the decision boundary. So basically, if you have, say, images on both sides of the boundary, and this is where you're shifting from one class to another, that will actually introduce more sharpness, let's say, in the model. So basically, you will need less noise to attack it.
Yeah, so you've answered the question. Sankur says that is very well explained. And then somebody's put the remark bias variance trade-off. Yasti is saying that she'll share the links and the material. Maybe we'll give her a paragraph in the newsletter that she sends out to 1,200 people. Okay, I think, any more questions, anybody? And please thank Irina for her talk if you liked it in the chat.
Thank you for joining.
If you find it helpful. Any more questions? Okay, people are thanking you. And I'll leave the chat open for a minute or two longer in case anybody has any questions. Looks like you've satisfied. Oh, can you do a quick demo if it's not too much trouble? Irina, I'm not sure what you can demo, but oh, okay, yes.
Yeah, so I can try to run a demo, but I'll just need a quick second. Okay, so let's see if we can get the demo running. Okay, so here we're gonna do an attack on an image. So we're taking a standard image recognition model that you can actually download from the internet, VGG16. And let's try to see. Yeah, and we upload an image to this. Here, the attack is going to be the fast gradient sign method, which is one of the fastest attacks. And you'll see that even this way, it does take a while to perform the attack. So this attack is kind of a quick and dirty. You will actually be able to see the noise in the image. While, for example, if you take attacks that run longer, then you wouldn't be able to see the noise almost at all. Okay, so here what you have on the left side is the original image, and it gets correctly classified as a bald eagle with 99% confidence. In the middle, you have the noise that was added, and the right-hand side is the noisy image, and you can see just a bit the pattern of the attack. And now if we take the same model, but we're gonna add one defense to it, and it's a defense that doesn't modify the model in any way. It's just doing some pre-processing step to the data, and that is just apply a smoothing filter. And we're gonna do the same attack again while applying the smoothing filter. So I'm mentioning that VGG16 is a model that you can download off the internet, because this way, I mean, you know that the model has not been tampered with. This is normally a correctly functioning model. Okay, so the same original image on the left, but now what you can see is that you can see the attack noise on the image, but the decision of the model has gone back to the correct decision, although with much lower confidence this time. And we also have a nice feature here. It's kind of a heat map on top of the image, showing pretty much what areas of the image justify the decision of the model. So you can see that this area shifts a bit.
Wow. So that's by adding the filter from the toolbox, you were able to overcome the attack.
Yeah, yes. But I mean, again, this kind of filter will work sometimes, but not in all cases.
Goodness, but that's a great on-the-fly demo. Thank you so much.
Sure. Are there any more questions?
I don't see any more. Any more questions, anyone? Okay, more thank yous. No more questions. So that was a wonderful session, Irina. Thank you so much, and I hope through these sessions we'll develop a very nice community around the toolbox. So thank you, everybody.
Thanks, everyone.
And thank you, Irina. And see you next week.